conditional probability. So now we want to talk about, okay, if you're given extra information, right? So how does your estimation, or how does the probability of an event change given extra information? Okay, so that's what we're going to talk about, conditional probability. All right, so let's do this. Let's just start with an example. So let's say I toss a coin 3 times. Okay, so first question, let me ask you this: what is the probability of getting 3 heads? What would you say? Okay, let's see, I have 1 answer, 1/8. Any other options? Any other answers? Okay, I'll give you a few more moments to think about it. Everybody 1/8, right? So in the experiment there are 8 possible outcomes, right? So 2 possible outcomes for each toss. So 2 times 2 times 2, we have 8, and all of them are equally likely. So we have 1/8 for each outcome. So 3 heads is one of the outcomes, so the probability should be equal to 1/8, right? So now let's say I will tell you that the first toss was heads. Okay, so then basically I'm asking you, what is the probability of getting 3 heads given the first toss is heads? That's the notation. H1 means the first toss was heads. That's the event. H1 is the event, the first toss is heads. So given that the first toss was heads, that you already know that, okay, now what would you say the probability of getting 3 heads is? 1/4. Okay, how did you guys come up with that?
Each toss is mutually exclusive.
Each toss is mutually independent. That's what that's what you're looking for.
So you just pretty much assume you have 2 tosses.
Okay. All right. Okay, yeah, that's one way to go. So we know that the first toss is already heads, right? So then only 2 options left, right? And there are total 4 ways to do that, right? And all of them are equally likely. Therefore, since there are 4 outcomes, each one of them will have 1/4 chance to get, right? Okay. So what is the probability of getting this? Heads, 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 given the first toss was tails?
0.
Okay, so if somebody tells you the first toss was tails, and then ask you what is the probability of 3 heads, you already know it's not 3 heads, right? So the probability of getting 3 heads is 0. Okay, so now let's look at a bit more methodological way of doing this. Okay, so let me list down all the possible outcomes. Let's see, so we go from, it's easier to write 1s, 0s, so I'm going to use tails for 0s. Heads I'm going to replace with 1s. Okay, so 0 0 0 0 0 1 0 1 0 0 1 1, and then 1 0 0 1 0 1 1 1 0 1 1 1. Okay, so this is heads, heads, heads. Okay, so now what we're looking, the way we are doing this in our minds is, when I say the first toss was heads, somebody already tells you if the first was is heads. Let's say this is toss 1, toss 2, toss 3, right? So that means when somebody says you that, that means that event is made of these guys, these 4 outcomes, right? So these 4 outcomes is a subset, viewed as a subset is H1. Everybody agree with me? Okay, so that's H1. And then when we say, okay, somebody is telling you the first one was a head, so that means you're only looking at these 4. Okay, so you know all the outcomes are limited to these outcomes given that information, and you know that each one of them could have happened equally likely. According to the given information, you don't have any bias against any of these outcomes, right? But you do have a bias to limit your view into these guys, and the 4 of them, that's why 1/4, right? Also, another way of looking at it is the outcome, the event you are looking for is this set. Okay, and the given event is this set. So the way we are defining the probability is H given H1, okay, is the probability of this event intersection this event divided by the probability of this event H1. Right, so that means given this, we're looking at in the numerator the probability of both of them happening jointly, right? And you're dividing that because your entire space of outcomes is just H1, right? Because you only have to look in H1. Previously you're looking at all omega, right, with all the whole entire set of outcomes. Now you're only looking at this one, that is H1, right? So that's why you normalize with the probability of H1. This is now your universe because it's already given to you. And then given this, how many times does H1 happens within this region? You guys get the intuition there on how we are coming up with conditional probability? So let's try to generalize this to more like a concrete definition. What we are going to say is probability of event A happening given event B happening, given event B has happened, is equal to probability that they both happen simultaneously divided by the probability of B. Right? Obviously, you cannot have this definition if P denominator is 0. Right? So you're going to say probability of B is not equal to 0, given that. If that is 0, then you don't define conditional probability. Okay, and that makes sense, right? If P of B is 0, that means that event cannot happen. If the event cannot happen, there is no point of asking, given that happens, what about this? Okay, so that's our mathematical definition of conditional probability. So as we said before, we look at all events as subsets, right? So that means A intersection B is well defined according to subsets. So that will be a subset, and the probability of that is the sum of probabilities of all the outcomes in that subset. Okay, so given this definition, can you guarantee that P of A given B will be less than 1, less than or equal to 1? Yes? How?
Because there has to be some value for P of B.
Okay, so P of B can be less than 1. Can be less than 1, right? And most often it will be less than 1, strictly less than 1, right? So how are we guaranteeing that the fraction is less than 1? Okay. Alex?
That is less than or less than or equal to 1?
Less than equal to 1.
Well, B can't be equal to 0, so we know that B has to be some number greater than 0, but that doesn't mean A can't have a 0 probability, so the intersection, either the probability of B is 100% or there's some possibility of A with it. I'm just saying.
Think about it. Think about it. So I'll give you guys a few moments to think about it. Again, discuss in groups, 2 or 3, and then we'll talk.
What up, prodigies?
The intersection should be small.
Yeah. I mean, yeah. Probability B can't be 0. Yeah. It's gonna be smaller than 1. The intersection of P, A, and B is a subset of P and B. Yes, that's like the everything about P A plus P B should be 1. It's gonna be less.
It's kind of like
Good work. All that. Copy spot.
Okay. Do I have volunteers? Ted, want to solve it on the board? So, okay. So there are 2 things we want to stress here. First of all, obviously, intuitively is the proof correct? But while Ted is writing the proof on the board, also pay attention to technical details, right? All steps have to be rigorously correct. Okay. Ted, go on.
Now I'm going to stage fright. So
You can write it right there.
I?
Yeah, right there.
So the best example that I can think of, like off the top of my head, the most efficient one, would be like a Venn diagram kind of design. Not proportional, whatever. So you have the events of A and the events of B. So there's some number of events in A and some number of events in B. And let's say that there's at least one that happens in event
You
A
guys see
and B.
You guys see the shadow?
Yeah.
Yeah, we're used
to
to
it.
Huh?
Oh,
big shadow? So I'm not crazy.
That's
Okay.
how the board is. It's with the
That's not
Yeah, because it's the glass thing, yeah.
No, it's so weird. Yeah, the board is like the board is more.
Yeah.
So,
lightning here, literally.
sorry.
Yeah, it's weird.
I see why that's happening. So, when,
Ambient light.
if you just want to write on the board, I think you should switch off the projector. We cannot have one. So that's fine.
We'll learn.
We'll let you.
We'll learn this.
Yeah, go ahead. Go ahead.
So like, so as I was saying, we have one confirmed event that happens in both A and B at the same time. So we know that the probability of A and B together is itself equal to 1 at least. So saying that, and we go ahead and define how many events happen in B. Yeah.
Can you explain what you just said, at least that, and explain your thoughts?
So like in this example of an event, there is one event happening in both A and B at the same time. So in the example proof that I'm putting here.
Yeah, so
It's not a numerical one.
Yeah,
This
yeah.
object is one.
yeah,
Out of many ones.
So like you're saying that it happened at least one time, but that's not what the probability is. If you were displaying what one outcome would be that happened, that would be a different statement than the probability of the intersection of them happening. Does that make sense?
Yeah.
That can only be one if A and B all happen together.
Yeah, if A and B are completely overlapping that Venn diagram, that's the only reason that statement
Yeah.
is true.
Yeah.
But that's not what
What you could do for A and B to make it easier is make A like 1, 2, 3, and then B 4, 5, and then, or 3, 4, 5, and then have 3 be that thing in the center where the intersection is. Then because we're using 6 values, the 3 is going to be 1 out of 6 in the intersection. So the intersection A and B is going to be 1 out of 6.
Right. Okay.
You see? Okay, yeah. Good. All right, thank you, Ted. So first of all, I want you all to appreciate, how good Ted actually did here, because talking from there is very different than talking from here. Right? So we actually did pretty good. So let's do a bit more rigorous way. So I heard like many comments which were rigorously true, right? And that's the right way of proving it while you were discussing it, which is pretty good. I think we have some time. So is there any other volunteer who wants to prove it in a technically correct way? Say, okay, Hector. Again, pay attention to the technical details because this is something. Yeah.
I know that the overlap, so it's going to be less to probability of just overlap, so because there's only one element in the overlap.
Okay, the subset of must be smaller than equal to. Okay. All right. And this does everybody agree with that statement, or is there any technical details you want to focus on?
Well, that's it.
Pretty much, yes. I agree.
Well, PA intersection B isn't a subset. It's A intersection B that's a subset.
Okay.
That's,
It's not, yeah.
yeah. So
Yeah, but the subset of P of B that is.
No, probability.
yeah, probability can't be a subset. That's where. Yeah.
Well, okay.
Yeah. So take out the probability in front. Yep. And then just put A intersection B,
There you go.
and that'll be fine. Yeah.
Okay. Yeah, that's almost there. Thank you, Hector. All right. So these are the kind of technical details I want you to write. So when you say subset of P of A intersection B, P is a number. Probability is a number, right? Okay. So let me write down the more elaborate proof here. In fact, it's a straightforward proof. I'm saying elaborate. Right? Let's say, in general, if for any sets, if S1 is a subset of S2, according to the way we are defining probabilities on events, these are events, right? Then probability of S1 is less than or equal to probability of S2. Agree? Right, because it follows from the definition of P on events, because we are summing up the probabilities on all the elements in that, and the probabilities are greater than or equal to 0. So if you sum more elements, it has to grow bigger, right? And it can be equal to if all the things which are extra in S2 all have probability of 0, then it will be equal to, right? So for here, the way you want to say is A intersection B is a subset of B. Therefore, probability of A intersection B is less than or equal to probability of B. Okay? And therefore, that fraction is less than or equal to 1. So if in here, each step is well defined and rigorous, right? So those are the kind of details I want you to focus on. Now, why am I stressing so much? Because these things seems very straightforward, right? Sometimes many proofs will not be straightforward. And if you're not technically, if you don't make sure that you're technically correct in each of the steps, you can come to a wrong conclusion. You can prove many theorems which are actually not true if you don't pay attention to details. Okay? So, all right. Now, let's dwell some more on this. This is a multiple choice question. A and B are two events. So choice number 1, probability of A given B plus probability of A complement given B is equal to 1. B, probability of A given B plus probability of A given B complement equal to 1. And C, probably very important, none of the above. Okay, again, I'll give you guys a few moments. Pick one.
Are you asking which one's true?
Yes. we all know that probability of A plus probability of A complement is equal to 1. Right? Okay. We know this. Now, which of these above 3 are correct?
Do A and B cover all?
Nope. There's no such case. E and B are just 2 events.
Me too.
All you need to do is pay attention to the definition there. Definition of the conditional probability.
So you said there in this space there's only A and B, and there's an intersection between those.
No, A and B are just some events.
There's just some events.
Some events, and there's no additional information about it.
See,
It would be B, A could be there are other things.
Well, you said there's only A and B intersections.
Yeah, but they're
Is that A? I'm going to say A to the power C. Is that
A complement, yes.
So for B,
Okay.
when you say B,
yeah, for B, A given B
yeah.
is this.
Well, I mean, no, I see what you're saying.
Yes, team up into 2s or 3s. I want to hear more discussions.
wait, so, but I think it should be A because you won't be able to sum these two together. You can't add these two together. But if this equals P of B over P of B, then you can sum it. I think it's A. Because this is A and B, right? And this is
Right, but
and then this is not A and B. So then they, both of these, when you add them together, they end up being B. So PB over PB is 1.
This is the clarifying question. There are other things that exist in this space besides just these variables.
Well, if you think about it, if you have A and then A complement, that means it's great B.
Okay, I think that's enough time. Let's see. Answers. How many say A? 1, 2, 3, 4, about 5. Okay. How many say B? 1 says, 2 says B. Okay. How many say C? Okay, so if I add this up, there are only 7. Right? So
Yeah, it looks like about 7 of us.
okay. So let me do this again. I want this to add up to like 25, right?
It's 2 and a 5 right there.
So again, how many say A? Okay, this time a lot more. Okay, and let's see how many say B. B says 3. Okay, 3 and everybody else, right? Everybody else. Okay, so people have said, like people who said B, explain to people who said A why B is correct. Tito.
I went with B because I was having a discussion with him. We didn't get to necessarily proving either statement. We were just talking about the concept of complement, and I was talking about if you have like technically B complement is all of A, right?
Why?
So that's what the fact that we were debating is B complement technically all of A?
Why?
It's not, because you could encompass some part of that.
Right. So what I'm saying is the complement B.
So,
B complement.
Joe has something to
Yeah,
say.
go ahead,
I
Joe.
wanted to say that when you're looking at something given B, we have to know what B is doing. So if we're looking at what B is doing in one direction, and then the opposite of what it's doing in the other direction, the combination of those two shouldn't work.
Why? But you know, I think what you're saying applies to this, right? You can replace A with B. You can say either B happens or B does not happen. Those are the only options, right? So, all right, let's. I think A is correct. Not I think, but A is correct. Let me, before we prove it, try to interpret this in terms of explaining this, right? So what does this mean? Given that B happens, this is the probability of given that B happens, A happens, and this is the probability that given that B happens, A does not happen, right? So again, given that B happens, either A happens or does not happen. There are no other options, right? So that is correct. If somebody tells you B happens, then the only two options are either A happens or A does not happen. If this is probability of A happening, this is the probability of A not happening. They have to want. English, just intuitively, that's all. Next thing we'll do is we'll prove it. Alex.
I feel like I'm wrong, but I'm still going to say this anyways. Isn't this still all contained in the probability of B though?
Why?
Isn't this the probability of A happening contingent that B has happened?
Right?
So if A happens,
Just be like the new subset. Didn't you say something like that?
Right. But we're only looking at the so A doesn't have to be contained within B.
you know what? Screw it. I mean, all we're really looking
it makes a lot more sense when you look at it.
is whether
Right.
A
like-
So that was the case in the example we're looking at, but that's not necessarily the case all the time. Okay. All right. So let's prove this. So let's prove A. So probability of A given B is probability of A intersection B divided by probability of B, right? And then plus probability of this one is probability of A complement intersection B divided by probability of B, right? Now these two sets, A intersection B and A complement intersection B, are disjoint. There cannot be anything common in them, right? So that means I can write this as probability of A intersection B plus A complement intersection B, because these two sets are disjoint. And by plus I mean union, sorry. Right? So A intersection B union A complement intersection B is B. Okay. All right. So if the only step, if I give you this and ask you to prove it, the only thing you have to do is start from the definition and then just use set theory rules. Right. And the intuition which I just said, we use that to interpret the result. But if you just follow mathematically, you'll get there, right? You don't even need to interpret intuitively what's going on. Just follow the rules, you'll get there. But it's important for us to interpret intuitively because that will give us a sense of how to apply it. Okay. Okay, Ted.
I just have a curiosity sake question. So what's the actual annotation for that P A line B?
It's probability of A given B.
A given B? Okay.
Right. Or you can also say probability of A conditioned on B.
Okay.
Okay, something like that. Or conditional probability of A given B. Something like that. Okay.
Wouldn't the bottom part A there, you went from the things being added together to the union?
Right. So it should not have been plus because these are subsets, right? It should have been union all the time.
Okay. So we shouldn't have been using
Right.
plus.
Again, that was a thing which you could have gotten quarter points for.
What?
do that?
Yeah, did you set it
What?
back?
No, I did not do that.
Yeah, they might be in the other room. So if we turn it off, they turn
Or by that, do you mean at the beginning of the problem, the plus was meant to be a union, or just
No, this plus is still plus. This is a union. So this plus is plus because these guys are numbers, right?
Yeah.
This is a union because these are sets.
oh,
Denial.
Okay, so I get how you get the probability of B at the bottom, but I'm confused that going from probability of A intersection B union A complement.
Okay. So we're going to focus a little bit more on this next because that's a nice segue. But let's say if this is A, right?
like that.
So this is A.
Okay.
And let's say this is A. How do you say? Okay. Let's say. Okay. Right. So let's say this is B. I don't think we can do anything else. This is the entire set omega. Okay. A intersection B is this part. Right, this is A intersection B. A complement is all the stuff which is not in A, right? So A complement intersection B will be this part. Okay, so that means A intersection B union A complement intersection B will be entire B. If you want to write it in more like precise English terms, A intersection B will have all the elements which are common to A and B. A complement intersection B will have all the elements which are not in A but in B. Okay, if you put them together, you should get all the elements in B. So that's actually a nice segue into what we're going to talk next.
So A complement wouldn't be everything that is B, but also not some part of A, so not any
Right.
section.
A complement will be this entire thing, right?
Okay, all right, yeah, that's what I was clear.
And A complement intersection B will be that. Okay. And before we wrap this up, there's another notation, and which we call if you start from here, you can go to P of A intersection B will be equal to P of B times P of A given B. Right? That just follows from the definition. And when we write it this way, we will call this the multiplication rule. Okay, and the way you read it is P of A and B happening simultaneously is equal to probability that B happens and probability that A happens given that B has happened. Okay, and with the same logic, you can also say this is equal to P of A times P of B given A. Again, this follows from the definition of P of B given A. Okay, and P of A intersection B is what we call the joint probability of A and B. Sometimes we also denote it as P of A comma B. Any questions so far? This is just for everything is following just from the definition of our conditional probability. Okay, all right. So next topic is probability of yes. This is just a notation, P of A comma B. Yep. Because sometimes we don't want to write intersection, we just say comma. Okay. So now, law of total probability. Does that ring a bell? Okay. So All right, it has two parts. First is, let's say, B1, B2, so on up till Bn are disjoint. That means all pairwise intersections are empty, right? And B1 union B2 union so on up till Bn is equal to omega. Okay, so that means you put together all of them, you'll get the entire set. Okay, and such a division of omega into subsets is called a partition. So we say the set B1 so on up till Bn forms a partition of omega.
I just want to make sure that I'm reading that right. The first line, B1, B2, Bn are disjoint?
Mm-hmm.
Okay. I just cut.
Yeah.
That's not right.
I know I have like super awesome handwriting. I have a T-shirt with that, by the way.
Is it in your handwriting?
So anyway, disjoint means they're pairwise empty intersection. Okay, so and then they all union up to omega. Then here's the statement of the law, which says probability of any event A will be equal to sum of probabilities of Pi times A intersection Bi. That's the law. I equal to 1 to n. Okay, so it seems like a complicated thing, but you know what, this is what that is. I can write A as A intersection B1 plus A intersection B2, sorry, union, so on up till union A intersection Bn, right? No, these guys are intersections. So this is just an extension of what we just discussed with A and B here in this diagram. So A and A complement are disjoint, and when you take the union of them, you get the entire set omega. Right? So here there was only two sets, now here we are going to n sets. Right? And the document which I'm going to upload also has a nice image to go along with it. I'll show that. Okay, see that. So here they have three sets, B1, B2, B3, right? They're all disjoint, that means they don't have anything in common. Pairwise intersection is empty, right? And this is A. And so A intersection B1, A intersection B2, B intersection B3. The union of all of them will be A. Right? So that's basically what the theorem says. If you take A intersection B1, A intersection B2, A intersection B2, union them up, you'll get A. Right? If you want to do that, but B1, B2, B3 have to cover everything. Right? If they don't cover everything, there may be something in A which you may miss. Okay? And they have to be disjoint, otherwise you'll be counting something twice. So that's the law of total probability. Okay, so from this step then you can just say probability of A, because now A intersection B1 is disjoint with A intersection B2, is disjoint with A intersection Bn, right? These subsets are also pairwise disjoint because B1, B2 are all pairwise disjoint. Everybody with me? Is that statement confusing? Okay, so that just means P of A will be sum or I P of A intersection Bi. Okay, and then I will use in the multiplication rule which is P of bi times P of A given bi. I can also write it like this, but okay. Oh,
Yeah, you were right.
yeah. So this was not correct. It should have been A given pi. Okay, yeah, Sangha.
So if they were not disjoint, would you just subtract the duplicates?
That's right. Right, and then that means there'll be this negative P of A intersection B1 union, intersection B2 and all that, there'll be lots of mess. That's why it's important to have disjoint events.
You wrote I equals 2 under the summation. I was wondering if I could get some clarification likewise. Oh, is that a 1? Oh, I totally read that wrong. I see.
Oh yeah, this is 1, not 2.
Oh, my, yeah, totally me.
Thank you. Okay. Last total probability. Any questions on that? Okay, then that's a nice place to stop.
Yeah, I feel like you should read it.